Hi all, welcome to Go Classes. Before we start, please tell me audio, video, volume, echo, is everything clear? Let me know. We are going to discuss today's DPP, the detailed solution with complete analysis. And today we have a beautiful question with us. Question from IIT Kharagpur. So let's start. Hi all, welcome to Go Classes YouTube DPP series for GATE CS, GATE DA, GOT DPP series. Today's DPP is subject discrete mathematics, topic functions, and the question is taken from IIT Kharagpur. This is a beautiful question, and when I saw this question, then I thought that maybe in the future GATE exam, this question might come. Go to DPP series, the complete playlist link you can find in the description, also in the pinned comment. Go classes YouTube DPP series, or aka GOT DPP series for GATE CS, GATE DA. All the questions are taken from standard resources to ensure that you practice top quality questions. On YouTube, you can search GATE CS DPP Go classes. On YouTube, in the search box, you can put GATE CS DPP Go classes, and our playlist will show to you. Okay, so you can see this is the complete playlist. View full playlist. You can see GOT DPP series GATE CS. The complete playlist, you can check it out. If you see any video of our GOT DPP series, then you will see that in the description, this playlist link is present. Okay, so on YouTube, in the search box, you can put GATE CS DPP or GATE DA DPP Go classes. Okay, and this playlist link, this DPP series, the complete playlist link you can find in the description, also in the pinned comment. A very important announcement for the GATE DA aspirants, that for GATE DA, we have also started the DPP YouTube DPP series. So on the Go Classes GATE DA YouTube channel, remember, Go Classes has GATE DA YouTube channel. Also, we have GATE CS YouTube channel. So on the Go Classes GATE DA YouTube channel, you can find the GATE DA YouTube DPP series. Okay, you can see the complete playlist link also you can find in the description, also in the pinned comment. So visit the Go Classes GATE DA YouTube channel and subscribe to it, and you can find the GATE DA DPPs there. This is our question for today. The source is IIT Kharagpur, and this is a beautiful question. In the future GATE exam, this question might come. First, we will understand this question, what this question is saying. Before solving the question, we need to understand the question. Most of the students, they will not be able to understand the question, so forget about solving it. So remember, the first step to solve any question, that is to understand the question. Now, this question has basically four options. This is MSQ question, means one or more options are correct. So if you did not try this question yet, means if you did not do this question by yourself so far, then you can pause the video, you can try this question on your own, you can write your answer in the comments below. Now I will provide you the detailed video solution with complete analysis. Let me tell you, this looks like a single question, one question, but these four options, these are like four questions. Each option is a different question. So I can say that today we have total four questions from IIT Kharagpur. Okay, now let's solve this question. For a function f, small f, for a function small f from set A to set B, define a function capital F from power set of A to power set of B as, you can see, f of s, this capital F of s. So what is this s? Because this capital F, this function is from power set of A to power set of B. So you can see this s, this is basically element of power set of A. Element of power set of A means this s is basically subset of A. Element of power set of A, that means subset of A. Okay, so you can see that f of capital S, this is basically For every element of capital S, you find the small f image of that element. Okay, so you can see this is capital F of capital S. Don't worry, we will understand. This might be confusing. This first line of the question, this might be confusing to many students. Many students will not be able to understand this first line, so they will not be able to solve this question further. I just want to tell all those students that before solving the question, you must try to understand the question. You can take a small example, you can take small set A, small set B, and then you can try to understand this question first. Okay, maybe you can spend maybe 5 minutes, 10 minutes, 15 minutes you can spend just for understanding this question. Once you clearly understand this question, what this question is saying, how these functions are defined, then you can solve this question. Okay, so now first we will understand this question, then each option we will take as a separate question and we will solve it. Okay, so let's start now. First, let's understand this question. We have a function small f and we have a function capital F. Now, here actually I don't want you to confused. I don't want to confuse you between small f, capital F. So let me do one thing, that this capital F, let me call it G. Okay? See, I don't want you to confuse between F F, because one is small f, another is capital F. So let me do one thing, that let me do let let's assume that this capital F, this is G. Okay, small f is small f, and this capital F, let me assume this is G. Okay, to remove the confusion, to remove F, capital F confusion. Okay, so anywhere if I write capital G, it simply means I am talking about capital F. Okay, if I write F, then I'm talking about small f. I hope you understood. Now let's see this question and let's understand this question. So you can see a function f is given to you from set A to set B, and with respect to this function f, another function f, capital F, means I can say capital G. So you can see another capital F function is defined from power set of A to power set of B, and this is how the mapping is defined in the capital F. Okay, now onwards I will assume that capital F means capital G. Okay, so now let me explain what this question want to say. We will take some small examples and then we will understand this question and then we will solve this question. So first, let me assume that set A, let me assume that is only two elements. So let me assume small a, small b, and let me assume that capital B, this is x comma y. Okay, so basically a small example I am taking here. Now the question is saying that we have small f, this function is there from set A to set B. Okay, so remember, from set A is AB, and set B, that is xy. So from set A to set B, there is a function small f. Okay, and the question is saying that we define this capital G, or I can say capital F, basically capital F, let me call it capital G. So this function we define from power set of A to power set of B. Now what is power set of A? You already know power set of A, that means set of all the subsets of A, correct? So I can say the power set of A, it will be having phi, basically all the subsets of A, the collection of all the subsets of A, that is power set of A. So I can say phi will be there. You can see this A will be there, this set containing B will be there, and this set containing AB will be there. So you can see this is power set of A. Now what is power set of B? You can see phi will be there, set containing X, set containing Y, and you can see set containing XY. This will be there. Now this is our power set of A, this is our power set of B, and now from this power set of A to power set of B, this function we are defining, this capital F, or I can say this capital G, this function we are defining. And how this mapping is happening? So remember, this capital F function, or I can say this capital G function, this is defined with respect to this small f function. So let's assume first, let me take this small f function, then I will take this, then I will find this capital F function. So let me assume that A is mapping to X, and let me assume that B is mapping to Y. In this small f function, let me assume this is the function. Okay, A mapping to X and B mapping to Y. Now let's see what will be the mapping of this capital F function. So the question is saying that capital F of any element in the domain, of course. So you can see this as this belongs to power set of A. Any element that belongs to power set of A, that is subset of A. Yes or no? So you can see that for any element in the domain, what will be the mapping capital F? So that is given to you. The question is saying that capital F, okay, or let me capital F of capital S, okay, capital F of capital S. So let me just write it G of capital S. What is this? This is small f of small s, where small s belongs to capital S. Okay, now let's understand this. Basically, let's see what will be the image of this element, because remember we are finding what will be the mapping of capital F, or I can say capital G. So let's see what will be the image of small a. So you can see, if I assume that capital S, that is set containing a, then what will be the image? So I can say image will be in this S. For every element, you can see small s belongs to capital S. Basically, for every element that belongs to S, you just find its small f image. Okay, see, very simple point, that for example, for this element, let me find what will be the image. So you can see, if I want to find the image for this element, the capital F image, if I want to find for this element, then what I need to do, in this set, for each element I will find the small f image. I hope you understood. Very simple point. Remember this point that I want to convey. You can see a function f, small f, is given to you from set A to set B, and with respect to this function f, another function capital F is defined from power set of A to power set of B. And this mapping is defined like this, that capital F of capital S, this is basically a set. You can see, for each element small s of capital S, you find the small f image of small s. Okay, see, this is actually very easy to understand, that we are basically saying that what is the capital F image of capital S. Of course, this is element of the domain, so this belongs to power set of A, correct? So you can see this S, this is this is in this is in domain of capital F. Okay, what is domain of capital F? That is your power set of A. Now you can see, if S if S belongs to power set of A, then what it means? Then it means that S is basically subset of capital A, correct? So you can see this capital S, remember this capital S, this is subset of capital A. Okay, subset of capital A. So I can say, for example, let me take example. Let's assume that this capital S, this is, for example, let's assume A1, A3. Okay, then in that case, this capital S, this is subset of A. So you can see here A is A1, A2, and so on, AN. Okay, this is your capital A. So you can see that this capital S, this is subset of capital A. Now, if I find what is the capital F image, the capital F image of capital S, then what that will be? So how to find it? Very simple. You can see, for each element of capital S, means for this element, for this element, for each element of capital S, you find its small f image. Means what you do, for each element of capital S, you find its small f image. So it's like, small f image you find for A1, small f image you find for A3. I hope you understood. Simple point. Okay, so very simple. Remember, for example, another example, let me take. If I take, for example, A1, A2, A4, then what will be capital F of S? So very simple, that for each element of capital S, for each element, you find its small f image. Okay, so you can see, you find what is small f A1, what is small f A2, and what is small f A3. So this is the point. I hope you understood this point. So very simple, correct? Now let's come back to our example. So here you can see this is the small f function that we have taken just for understanding purpose. Now, in this case, what will be the capital F mapping? So here you can see for 5, what will be mapping? You can see if I ask you what will be the mapping for 5. 5 means empty set. So you can see basically capital F means capital G. Okay. So if I ask you what will be the mapping of 5, then that will be 5 only. Because in the 5 there is no element. What is 5? 5 is empty set. Okay, so in the 5 there is no element. See, very simple. You already know that the capital F of any set. Okay, if I take any set, for example, like A1, A2, if I take, then what that will be? You already know that will be basically for each element you find its small f image, correct? Okay, so I can say small f A1, small f A2, right? But if I ask you that for this empty set, what is this? This is basically empty set. For this empty set, you can see there is no element here. Here there is no element. So this empty set you will get, because remember, if there is element, then you will find its small f image. If there is any element, for each element you will find its small f image. But if there is no element here, then image will be phi. So very simple, that capital F of phi, that will be phi only. Okay, simple. For all other set, what will happen? Whatever other set you take, for example, if I ask you what is capital F of A1 only, means set containing A1, what will be the image? So very simple. For this element you will find small f image. Okay, so simple. I hope you understood this point. So I can say that for this phi, the mapping will be phi only. Okay, phi will map to phi. No one else will map to phi. What is the reason? Tell me. You can see phi will map to phi, but no one else will map to phi, because for everyone else, what you will do? For each element, you will find its small f image. And remember that by the definition of function, you know, in the definition of function, what we say? We say that function is a mapping in such that for each element of the domain there is exactly one image in the codomain, correct? So you can see that image of phi will be phi. Phi will map to phi, but no other element will map to phi, because in all other elements there is in all other set there is at least one element. And you can see for this element you will find the small f image. So definitely you cannot get phi. Okay, because when you see the small f, then you can see every element of domain will map to exactly one element of the codomain. This is the definition of function. Whatever function you take, you don't have to take this function, you can take any function. So you can see that phi will map to phi, no one else will map to phi. Now let's see where A will map. A will map to x, because you will find the image of A. This B will map to y, because you will find the image of B. Okay, and where this AB will map? So here for each element you will find its small f image. You can see the small f image of A, that is x, and the small f image of B, that is y. So you can see that it will map to xy. Very simple. I hope you understood. So this is just one example that we have taken. Now let me consider another example. You can see I have same set A, B. Just for understanding purpose, I am taking small set here. Now let me assume that A is also mapping to x and B is also mapping to x. Now this type of function I am taking, this small f function I am taking, that A and B both are mapping to x. Now let's see what will be the capital F mapping. So very simple. Phi will map to phi. This is very easy. Now where this A will map, so you will find the small f image of A. So that is mapping to x. Now where this B will map, you will find the small f image of B. So this will also map to x. And now you can see you will find the for each element you will find the small f image. So you can see what is the small f image of A, that is x. What is the small f image of B, that is also x. So remember this AB, this also will map to x. So this will be your capital F. I hope you understood. Okay, so are you getting, are you understanding how these functions are defined? Now let me take another example. Let me take, for example, let's assume that set A, it has three elements. Let's assume it has three elements like A, B, C. And let's assume set B, it has only two elements, X, Y. Okay, this example we are taking. Now you can see small f. This is defined from A to B. Okay, here you can see this A. This is ABC, and this B. This is XY. Now you can see this is capital A. This is capital B. From A to B, we are defining this small f function. Simple, very simple. Now you can see what is this capital F function. This capital F function, or I can say this G. This is basically defined. This is defined from power set of A to power set of B. What is power set of A? This is the set of subsets of A. So you can see power set of B. Now here, because this set A has 3 elements, so in the power set of A there will be total 8 elements will be there, and in the power set of B there will be total 4 elements. Now let me just quickly take, here you can see power set of A. What that will be? There will be total 8 elements. You can see 5 will be there. Every subset of A will be there. You can see every subset of capital A. So you can see this A will be there, this B will be there, this C will be there. Then you can see this AB, AC, BC, and ABC. And you can see ABC. Okay. So very easy. Now this is the power set of A. And what is power set of B? That will have 4 elements. You can see phi, x, y, and you can see xy. Okay, so very simple. This is power set of B. Now remember, from power set of A to power set of B, this function g we are defining. Okay, now here, let's see, if mapping of small f is given to you, then what will be mapping of capital G? So let's see that. Here you can see, let me assume that A is mapping to x, B is mapping to y, and let's assume C is also mapping to y. Now in this case, what will be this capital F or capital G? What will be this mapping? Very simple. Phi will map to phi. This we have already seen, because in this phi there is no element. So you can see phi will map to phi. Now where this A will map, you can see set containing A. So for each element in this set, basically set containing A, in this set for each element you will find the small f image. Now you can see this small A, in this small f it is mapping to x. So you can see this will map to x. Now you can see where this B will, this set containing B, where it will map. You can see for each element you will find the small f image. So you can see B is mapping to y. So you can see this will map here. Next, what about this C? This will also map here. Now, what about this AB? For each element, you will find its small f image. You can see small a mapping to x, small b mapping to y. Okay, so you can see that this AB, it will map to xy. Now, what about AC? For each element, you will find the small f image, A mapping to x, C mapping to y. So you can see this AC will also map to xy. What about BC? For each element here, for each element you will find the small f image, both b comma c, they are mapping to y. So you can see this set BC, this will map to y. Okay, and what about this ABC? For each element you will find the small f image. So you can see this A is mapping to x and BC, they are mapping to y. So I can say that this ABC will map to xy. Okay, I hope you understood this. So very simple to understand. So remember, set A can be anything, set B can be anything. So you can see they can have different sizes, no problem. Set A can have size 2, set B can have size 3. Everything is fine. Okay. And you can see this small f, this can be any function. Once you have this small f, then you can easily find this G, or I can say capital F. Okay, so I hope you understood what this question was saying. Please tell me, did you understand the mapping, how the mapping is done? So remember, before solving this question, first you must understand this question. At this moment, you just tell me, did you understand this question so far? Are you comfortable with this terminology, all these notations that are given to you? Please tell me. So very simple point. Let me just write it here. The conclusion, let me write. So let's assume that this set A, let's assume this is A1, A2, A3, and so on AN. Let's assume this is the set A. And let's assume that this set B, this is B1, B2, and so on Bm. Okay, so you can see that the size of set A, that is n, and you can see the size of set B, that is m. So very simple, that both these set, they can have any size. There is no restriction that their size must be same. That is not given here. You can see set A can be anything, set B can be anything. Now, what is this small f? This is a function from A to B. So remember now this small f, this is a function from A to B. What it means? It means that it means that this is the, you can see set A. It contains A1, A2, A3, and so on, AN. Okay, and you can see this is the set B. This has B1, B2, and so on, BM. Correct? Now, BM. Now you can see this F, this is a function from set A to set B. From set A to set B, this small f is a function. Now remember the definition of function. The definition of function says that function from set A to set B, this is a structure, this is a mapping such that every element of domain, every element of set A will map to exactly one element of codomain. Codomain is B. So you can see this A1, this will map to exactly one element. This A2 will map to exactly one element. This A3 will map to exactly one element. This AN will map to exactly one element. Each element of the domain will map to exactly one element of the codomain. Remember, different elements can map to same element or different element. For example, this is perfectly fine. But you can see each element of the domain is mapping to exactly one element of the codomain. So from the domain point of view, each element will map to exactly one element of the codomain. But remember, different elements, they can map to same element or they can map to different element. So this is perfectly fine, no problem. So this is the definition of function, you already know. Now you can see this small f, this is a function from set A to set B. Now with respect to this small f, a function has been defined, that is capital F. So you can see the question is saying that now we are defining this capital F function, which we will call capital G. And this function they are defining from power set of A to power set of B. Now remember, power set of A, that means collection of subsets of A. So in the power set of A, you will have subsets of A. In the power set of A, you will have phi. Okay, you will have subsets of A. For example, you will have this subset of A. For example, you can see this A1, A3, this is also subset of A. Are you getting my point? So very simple. And you can see, and so on. This entire thing means this A1, A2, and so on, AN. So you can see that this is the power set of A. And from power set of A to power set of B, what is power set of B? That is set of subsets of B. So all the subsets of B, for example, phi. Okay, for example, you can see this B1. For example, you can see this B2. Okay, for example, I can say this B3, B5, B3, B5, like that, and so on. Okay, and at the end, the entire this set B also, yeah, I can write. Okay, because this B is also subset of B. So, for example, this is capital A, this is capital B. So overall, now you can see that from power set of A to power set of B, this is power set of A, this is power set of B. From power set of A to power set of B, this capital F function has been defined. Okay, and what is the mapping in this capital F? The mapping is like this, that if I ask you that capital F of any element of domain, capital F of any element of the domain, for example, let's assume, take this element of the domain A1, A3, take this element of the domain. So you can see, take this element A1, A3, then what will be the image here? So remember, for this element in the domain, this is our capital S, I can say. So you can see, for this element in the domain, what will be the capital F image? So that is very simple, that you find for each individual element, means in this set, for each element you find the small f image. Okay, so for example, let's assume that A1 is mapping to B1 and A3 is mapping to B2. Now in this case, you can see for each element you will find the small f image. So what you will get? You will get B1, B2, you will get. Okay, I hope you are getting. So you can see that basically for each element you will find small f image, means small f of A1 and small f of A3. So this is what you are going to find. Remember, they can be same also. For example, maybe a1 and a3, maybe they are mapping to the same element. It might happen, correct? So it may be possible. You can see it may be possible that a1 and a3 both are mapping to b1. In this case, remember, this f a1, this f a3, they will become same. Means I can say that for this element a1 a3, the image will be simply b1. Okay, I hope this point is clear. So very simple point. Now, so you can see that if this type of situation happens, that a1 is also mapping to b1 and a3 is also mapping to b1. In this case, you can see that this a1 a3 will map to b1. Okay, because you can see this simply will become b1. So that's it. This is the idea. I hope you understood the idea. Now I can write in the formal words. Okay, like in the question. So you can see the question was basically saying that capital F of capital S, what that will be for each element in the capital S. Means this capital S, this is element of power set of A. So this capital S, this is basically subset of A. This capital S, this is basically subset of A. So you can see that this capital S, this is a set of elements. So you can see for each element in the capital S, for each element in the capital S, you find the small f image of that element. Okay. So this is how these functions are defined. I hope you understood. Now, once you understood this question, then let's solve all these four options. Let's check each of them separately as a separate question. So let's take the first one. If capital F is injective, then small f is injective. We need to check whether this is true or false. I don't know whether this is true or false. I don't know. But let's check. If capital F is injective, then small f is injective. Then we also need to prove, or I can say we also need to find whether this is true or false. Means if small f is injective, then capital F is injective. Basically, both the directions we need to check. If small f is injective, then what can you say about capital F? If capital F is injective, then what can you say about small f? So these are the first two options. Now, first let's check the option A. You understood this? The complete question you understood? The notations, everything you understood so far? Now let's see. Now let's see the option A. Let's check this. So you can see this option A. This is saying that if capital F, if capital F is injective, then small f is injective. Okay. Now let me tell you, this statement is actually true and we need to prove it. This statement is true, and with by contradiction we can easily prove it. First, you understand the definition of injective. What is the meaning when I say capital F is injective? The definition of injective function basically says that different elements will map to different elements, correct? So very simple. You already know the definition of injective function. So let me just write it here. Let's see this recap basically. What is a injective function? What is a injective function? The another name for injective function, that is one function. Okay, so one function, this is another name for injective function. So what is injective function? You can see f from A to B, this function f, this is injective. When can I say this is injective? If and only if different elements have different images. What it means? Different elements have different images. It simply means that, it simply means if you take two different elements from the domain, then their images will be different. Okay, so I can say this function f is injective if and only if for all elements xy in the domain, for all elements xy in the domain, what can I say? I can say that if x and y are different, if x and y are different, then their images also will be different. Means fx and fy, they also will be different. Okay, so this is the idea. I hope you understood. The same thing I can also write contrapositive here, because you know this is the implication statement, and every implication statement that is equivalent to its contrapositive. Okay, so I can say that I can also write like this, that for all x y, for all the elements, for any two elements belonging to set A. Now I can say if fx and fy are same, then x and y also will be same. So I can say that if fx and fy are same, means if their images are same, if their images are same for xy, if their images are same, then I can say that these elements are also same. I hope you understood. This is the definition of injective function. Injective function simply says that different elements have different images. Okay, this is the simple idea. Different elements, different images. Different elements, different images. Different images. Okay, so very simple. If you take any two elements, if they are different, then their images will be different. Or I can say for any two elements, if the images are same, then elements will be same. So this is the definition of injective function. Now once you understood this injective function, then let's see this option A. Now let's prove this option A. If capital F is injective, then small f is injective. Now here this is given to you, that capital F is injective. This is given to you. So here what we have, let's write what is given to us. It is given that capital F is injective. Okay, this is injective. So now we need to see, can I prove small f is injective or not? Okay, so first you understand, when it is given that capital F is injective, what this actually means. You already know that this small f, this is from set A to set B. And what is this capital F? This is from power set of A to power set of B. Correct? Okay. So now, when I say capital F is injective, it means that if you take any two elements from the power set of A, any element in the power set of A, that is subset of A. Correct? This is the definition of power set, that any element in the power set of A, that will be subset of A. So basically, if you take any two subset of A, or I can say if you take any two elements of power set of A, then their images will be different. If the elements are different, their images will be different. Correct? Okay, this is the definition here. Now this is given to you that capital F is injective. Let's assume that small f is not injective. Okay, let's assume, for contradiction, let me assume that small f is not injective. Okay, are you getting my point? So this is what I need to prove. I need to prove, remember, I need to prove that small f is injective. Small f is injective. This is what I need to prove. But to prove this, what I will do, to prove this, for contradiction, I will assume. Basically, by contradiction, I will prove it. So for contradiction, let me assume. Just for contradiction, let me assume. For a moment, let me assume that f is not injective. Now, if you assume, for a moment, if you assume that small f is not injective, what this means? This means that there are at least two elements in the small f, at least two different elements whose image is same. Do you agree? When I assume that small f is not injective, then it simply means that there are at least two different elements in the small f whose image is same. Correct? This is the idea. Okay, so you can see this small, let's assume this, in this A you have these elements like a1, a2 and so on, an, and in this B you have these elements like b1, b2 and so on, bm. Okay, now you can see, because you are assuming that small f is not injective, so what will happen? So now for two different elements, there are at least two different elements for which the image will be same. Okay, so I can say, fx. Now those two elements, you can assume that these are x comma y. Okay, so for x comma y, where x and y are different, for x, so for some x comma y, I can say, so definitely, so for some x comma y, such that x and y are different, their images are same. Small f is small fx equal to small fy. Correct? Okay, very simple. I hope you understood. Now you can see that these xy, these are different, but their images are same. So definitely I can say that f is not injective. This is what we are assuming, that small f is not injective. So this will happen. Definitely this will happen. If small f is not injective, then there will be some elements x comma y, at least two elements x comma y, such that they are different and their images are same. Now in this case, what will happen? Now you can prove that this capital F is also not injective. If you assume that small f is not injective, then you can prove that capital F also will not be injective. But already we know that capital F is injective, so our assumption is wrong. So I can say small f is injective. This is how we are proving by contradiction. Now, what is my task? My task is that if I assume that small f is not injective, then I can prove that capital F is also not injective. How? What is the reason? Let's see. So you can see, for assumption, basically, now let's continue here. So you can see, so in this capital A, okay, basically, because you are assuming that this small f, this is not injective, so there are at least two elements x y, there are at least two elements such that their images are same. Okay, their image is same. So let's assume that image, you can assume that, let's assume that image is theta. Okay, so you can see here that x and y, their image is same. Okay, there are at least two elements here. So this is the situation, right? In the small f, this is the situation. Now notice what will happen in the capital F. In the capital F, this capital F, this is from power set of A to power set of B to power set of B. So you can see, in the power set of A, you have this element, correct? This set containing x, this will be there, correct? Because you can see the domain of capital F, this is power set of A. Power set of A means the collection of subsets of A. So you can see, if this element belongs to capital A, then definitely this set containing x, this is a subset of A, or I can say that this belongs to power set of A. So you can see that this capital F, you focus, this is from power set of A to power set of B. So in the power set of A, you have this element also, you have this element also. Okay, correct? Now let's see what will be its image in the B. Okay, what will be its image here? So you can see, now let's see what will be its image in the power set of B, because remember here this is power set of B and this is power set of A. Now you can see, if this theta belongs to B, then this set containing theta, this will belong to power set of B. Correct? Okay. Now you just tell me one thing. What will be the image of this set? You can see, for this set, if I want to find the capital F image, the capital F image we are finding. So just tell me this point. For this set, for this element, what will be the capital F image? I told you how to find, very simple. For each element here, you find the small f image. Correct? So you can see, for this element x, what is the small f image? That is theta. So you can see this will map to theta. And for this element, what will be capital F image? So you can see, for this element, for each element here, you will find the small f image. So you can see y maps to theta. So I can say this also will map to theta. Now, did you notice? If you assume that small f is not injective, then this capital F is also not injective. Okay, so here, did you notice here, this capital F is not injective. And this is a contradiction. And you can see this here, this capital F is not injective. This is bringing you a contradiction here, because we have been given, it is given that capital F is injective, and you are saying that capital F is not injective. So definitely there is a contradiction here. Okay, and because the contradiction is there, it means our assumption was wrong. What was our assumption? Our assumption was that small f is not injective, so our assumption was wrong. So I can say small f is injective. Okay, is this clear? Because of this contradiction, because of this contradiction, we have proven that if capital F is injective, then small f is injective. Okay, this we have proven. I hope you understood. Basically, the how did we prove it? We proved it like this, that if small f is not injective, then capital F is not injective. This is how we proved it. Okay, basically, how we proved, what we did, how we proved. Basically, we proved the contrapositive. Basically, if small f is not injective, if small f is not injective, then capital F also will not be injective. Then capital F is also not injective. Okay, and remember, this is contrapositive. See, this is a conditional statement, this is implication statement, and you already know every implication statement is equivalent to its contrapositive. This is the contrapositive. Yes or no? So I can say this statement, this is basically contrapositive of A. This is contrapositive of option A. And we already know one thing, that any implication statement P implies Q, this is equivalent to its contrapositive, means negation Q implies negation P. This you already know. So you can see, basically, to prove this option A, we are proving the contrapositive, and of course the contrapositive is equivalent to its, every implication statement is equivalent to its contrapositive. So you can see that this statement, this is equivalent to the contrapositive, because you have proved the contrapositive. So I can say the original statement also you have proved. Okay, I hope you understood this. Okay, so that's it, we have done this first part. So this first part is true, means if capital F is injective, then small f will be injective. Let me just quickly give you the conclusion here for the option A. Okay, basically what we did for option A, just let me quickly tell you the summary, the conclusion, the summary. What we did here, the summary is that basically we proved that if f not injective, if f is not injective, it will imply capital F not injective. Okay, this is what we proved. Of course, this is contrapositive of the option A, but you already know every implication statement is equivalent to its contrapositive, so it's perfectly fine. Basically, this is what we proved, that if F is not injective, then capital F is not injective, and this is very easy to prove, because you can see the proof was like this, that if F is not injective, what it means, you already know that F is from A to B. So you can see this is A, this is B, F is from A to B. So you can see, if F is not injective, then what it means? It means there are at least two elements xy who will map to same element. Yes or no? At least two different elements xy are mapping to same element in the set B. Okay, this is the meaning of small f not injective. Small f is a function from set A to set B. So I can say, if small f is not injective, then in the domain there are at least two different elements who are mapping to same element in the codomain. Correct? Now you can easily see that from here, you can easily see that in this capital F, what will happen means, this is power set of A, this is power set of A, this is power set of B. In the power set of A, definitely this will be there. In the power set of A, these will be there. Yes or no? Okay, because this is subset of A, this is subset of A. So you can see this is power set of A, and you can see in the power set of B, this will be there, because this is a subset of B. So very simple. Now you can easily notice that if F is not injective, then what about the capital F? That also will not be injective, because what will be the image of this? You can see for each element you will find the small f image. So you can see this x will map to theta, and you can see this y will map to theta. So this is the idea. I hope you understood. So you can see, if you assume that small f is not injective, then you can prove that capital F also will not be injective, and this is contrapositive of the option A. So we have proved option A. This is the conclusion, this is the summary. I hope you understood. Is there any doubt in the option A so far? So remember, so far we understood this question, then we have solved this option A. So option A is true, and we have proved it. The proof was so simple. Did you understand? Let me know. Let's see option B now. Now we need to prove that if small f is injective, then capital F is injective. This is what we need to prove. So now let's see this option B, And option B is saying that if small f injective, then capital F injective. This is what we need to prove now. Okay, now let's prove it. See, you already know, if small f is injective, it means that for different elements there is different images, correct? We need to prove that capital F is also injective. Okay, so let's do this. First, you understood. First, you understand what is given to you here. So here, the given thing is that small f, which is from set A to set B, is injective. Now, small f is given to you as injective. What it means when I say small f is injective, it means different images have different images, different elements have different images, correct? So you can see that in this A, this is your function small f from A to B. Now, different elements of A have different images. This you already know. Okay, if I take different elements, for example, let's assume A1, A2, then their images will be different. Their images that will be different. That you already know. But one more thing you understand that if you take any element y, then it will have image fy, correct? You just tell me this element y, it has image fy, and because this small f, this is injective, is it possible that any other element can map to small f, uh, to this fy? Let me know. Very simple point I'm asking. It is given to you that small f from A to B, this function small f is injective, means different elements have different images. In set A, any two different elements, if you take, their images will be different. So you just tell me one thing. In this A, if this element y has image fy, can any other element of A map to this fy? Is it possible? Can any other element, can any other element map to fy? No, it's not possible. Yes or no? Can any other element map to fy? No, it's not possible. Do you agree with me? Because different elements, different elements will have different images, correct? I hope you understood this. So just remember this point, that because small f is injective, so for this y, the image is fy, and there is no other element of A, there is no other element different from y, there is no other element of A which will map to fy, correct? So this you understood. Okay, so basically this is what it means. Now let's see, if small f is injective, then what can I say about capital F? I need to prove that capital F is injective. How to prove capital F is injective? For that, what I need to do? That different elements of capital F will map to different elements. This is what I need to prove, correct? Okay, so now this is given. Now, what I need to prove? Let's see what we need to prove. We need to prove that capital F is injective. This is what I need to prove. Now, how to prove this capital F is injective? To prove this, what I will do? So, we need to prove that different elements have different images. Okay, so here, what to do? To prove this, you take two elements of capital F. Take two different elements of capital F. What is capital F? This is from PA to PB, power set of A to power set of B. Okay, so now you can see I need to prove that capital F is injective. What this means? This means that different elements, different images. So what you do? You take two different elements of power set of A. Take two different elements from the domain. Take two different elements in the domain. Okay, take two different elements in domain in PA. Okay, let's assume those two different elements, take two different elements m comma n in PA. So what we need to prove? We need to prove that because these are different elements m comma n, these are different elements in the power set of A. So what I need to prove? If I want to prove that capital F is injective, then different elements must map to different elements. Yes or no? So I basically need to prove that this capital Fm and this capital Fn, they will be different. Yes or no? This is what I need to prove. Okay, I hope you understood what I need to prove. So you can see small f is injective. This is given to you. I need to prove that capital F is injective. Capital F is from power set of A to power set of B. So what I will do in the domain, let me take two different elements. In the domain, I am taking two different elements, m comma n. These are two different elements in the domain. Okay, now if I want to prove that capital F is injective, then different elements must have different images. So I can say that this capital M, capital M, capital N, they also must have different images in this capital F. Yes or no? So this is what I need to prove, that capital F is not equal to capital Fm is not equal to capital Fn. Okay, yes or no? Now let's see how to do this. You just take M comma N, these are different, right? Now you can see M comma N are different. So you can see this capital F, this is from PA to PB, and you can see this M comma N, they belong to PA, and they are different. M is different from N. What it means when I say M is different from N? What it means? Remember, this M N, they belong to PA. What it means? It means that M is subset of A, N is subset of A. M is subset of A, also N is subset of A. Correct? So now, if they are different, what this means? This means that there is at least one element which belongs to one of them but not the other. Yes or no? See, M comma N are different. What it means? It means that there exists a element, there exists a element X. Okay, let me take that element X, or let me take that element Y. So you can see if M comma N are different, it simply means that there exists a element Y such that Y belongs to M and Y does not belong to N, or or Y does not belong to M and Y belongs to N. Agree? Because these two set, M comma N are set, remember. M comma N, they are basically set. They are basically subsets of A. Okay, they are basically subsets of A. So I can say they are basically set. So I can say if they are different, M comma N, if they are different, it means that there is at least one element which belongs to M but not N, or which belongs to N but not M. Yes or no? Either this will happen or this will happen. There is at least one such element which belongs to one of them but not the other. Correct? Okay, so you can take this case or you can take this case. Both are basically fine. Okay, yes or no? So let me take this case. Remember, the same thing will apply in this case also. Okay, basically the point is that if M comma N are different, then there is at least one element which belongs to one of them but not the other. Okay, yes or no? So now now you can see that, let's assume that M has this element Y. M has this element Y, and you can see N does not have this element Y. In N, you don't have this element Y. This Y element you don't have. Okay, here you have this element Y, and you can see N does not have this element Y. Do you agree? Okay, means this simply, I hope you understood that Y is not here. Okay, Y is not here. Correct? So you just tell me one thing, that what will be F capital M? What that will be? F capital M. So you can see for this capital M, what will be the capital F image? What you will do? For each element, you will find the small f image. Do you agree? Means you will find the small f Y. Okay. And here, what will be capital F N? So here, now you notice one thing, something interesting, that can I say that this element, whatever is this element, let's assume this element is theta. Can I say this theta will not belong here? What is the reason? Can anyone tell me what is the reason? See, very simple point. I am just saying that this theta will not belong to this. Theta does not belong to theta does not belong to capital Fn. What is the reason? Because small f was injective. See, remember one thing, that small f was injective. And I told you, because small f is injective, so this y will map to fy, and you already know that no other element will map to fy. Yes or no? Notice, this y belongs to capital M. Y does not belong here. And y will map to small fy. Y will map to fy. No other element can map to fy. Yes or no? This you already know. No other element maps to fy. So means these elements, they can never map to fy. So means fy will not be here. Okay, do you agree with me? So you can see this fy means this theta. This will not belong to capital Fn because the small f was injective. So only y maps to fy. Yes or no? No other element maps to fy. So I hope you understood that basically I can say fm fn, they are different. Is this point clear? So what I can say from here, so what we have proven, so we have proven that capital Fm is different from capital Fn. This is what we have proven, and this is what we wanted to prove. Yes or no? Okay, I hope you understood this. This is what we wanted to prove. You can see, we wanted to prove that capital Fm, capital Fn, that is different, and this is what we have proven. Did you understand? See, let me just quickly tell you the conclusion here. This is the statement, this is the option B, that if small f is injective, then capital F is injective. Now, already it is given that small f is injective. This is given to us. What it means? It means that for some element y, if the image is fy, then remember no other element will map to fy. Yes or no? So basically, you can see that only y maps to fy. Only y maps to fy. No other element maps to fy. Okay, correct. Only y maps to fy. No other element maps to fy. This is the meaning of small f being injective. Now we need to prove that capital F is injective. This is what we need to prove. To prove capital F is injective, what this means? This means that for any two different elements in the domain, their images must be different. So you can see the domain of capital F, that is power set of A. So you take two different elements in the power set of A, M, N. These are two different elements in the power set of A. Now I need to prove that their images also will be different. Means Fm, Fn, they are also different. This is what I need to prove. Yes or no? Now you can see that this Mn, these are different elements in the power set of A. Any element in the power set of A, that is subset of A. So you can see Mn, these are basically subset of A, and they are different. If they are different, if Mn they are different, it means that there is at least one element which belongs to one of them but not the other. There is at least one element, there is at least one element Y which belongs to one of them but not the other. Now, here you can see, let's assume that this Y belongs to M and this Y does not belong to N. So you can see, let's find the capital F image of M comma N. Then you can see, to find the capital F image, what you will do, for each element you will find the small f image. So you can see, for this Y, the small f image will be small fy. Now you can see that this only, we already know, only this Y will map to small fy. Now you can see these elements, they do not contain small y, because M and they are different. Y belongs to M, Y does not belong to N. So this here Y is not there. If Y is not there here, then these elements cannot map to Fy. Yes or no? These elements will not map to Fy. So I can say that here you will not get Fy. So I can say this Fy, this belongs to capital Fm, but it does not belong to capital Fn. So it means that Fm, Fn, they are basically different. This is what we wanted to prove. So hence proved. Okay. So that's it. I hope you understood this. Did you understand? Let me know. Let me know. Did you understand so far? This option B also. Did you understand? So let's come back to our question. So you can see this option B, this is also we have proven. I hope you understood this. Okay. So the proof, did you understand? Basically, small f is injective. So capital F also will be injective. Okay. Okay. Let me just tell you the summary. For option B, the summarized version, let me tell you. The option B was that is small f injective, then capital F injective. Let me just tell you the summary of the proof. The proof summary. Proof summary is like this. F injective, this is given. Small f, which is from A to B, this is injective. This is given to us. Okay. Then because this is given to us, so one thing I can say that this is A, this is B, and you can see this is small f. Now you can see one thing I can say that this y maps to fy, this y maps to fy, and no other element can map to fy. No other element will map to fy. Okay, correct? See, I'm making the diagram to help you understand. So you can see because small f is injective, so different elements have different images. So I can say that if y is mapping to fy, then no other element of A will map to fy. Yes or no? Only y maps to fy. Only y maps to fy. Okay, correct. Okay, very good. Now you can see, let's come to capital F. This is what we need to prove. This is what we need to prove, that capital F, which is from PA to PB, which is from PA to PB, is injective. Okay, this is what we need to prove. So, how to prove it? Very simple. You take two different elements of capital F, correct? Okay, so what you do? You take two different elements of capital F. Sorry, you take, how to prove this? You take two different elements of PA. Okay, two different elements of the domain you take. Okay, so you can see this is PA and this is PB. You take two different elements. Okay, let's take M, let's take N. So this is M, this is N, correct? Now we are take M different from N. Now this Mn we are taking. Now if Mn are different, then we can prove that their images will be different. Why? What is the reason? See, if Mn are different, Mn they are different, it simply means that there is at least one element which belongs to one of them but not the other. Okay, yes or no? Correct. So you can see, take M and N different. What it means? It simply means that there is at least one element. There exists a Y. There is at least one element such that Y belongs to M and Y does not belong to N. Correct? Okay. So you can see Y is belonging to M, but Y does not belong to N. We are taking two different elements of PA. Now you can see their images also will be different. This FM, and this FN. Their images, they will be different. What is the reason? Because you can see here you will have FY. See, they also will be different because in this, in this FM, there will be FY. But here you will not have FY. Okay, so very simple point that, so here I can say, so Fm is different from Fn. Okay, I hope you understood the reason. The reason is because this Fy will belong to Fm, but it does not belong to Fn. Okay, correct. What is the reason? Because only y maps to Fy. There is no other element which maps to Fy. Okay, correct. So I can say that here you don't have y. So no element here, because only y maps to Fy, and here you don't have y. So these elements cannot map to Fy. So I can say that here you don't have Fy, but here you have Fy. So this capital Fm, capital Fn, they are different. Okay, that's it. This is what we wanted to prove, that this capital F is injective, means different elements Mn, they are mapping to different elements. Okay, so this is the summary of the proof. Now let's see option C. If capital F is surjective, then small f is surjective. And option D, that is, if small f is surjective, then capital F is surjective. Let me tell you, these statements are also true. And now let's prove it. The proof is actually very simple. So let's see the option C first. Let's start with option C. Option C is saying that if capital F is surjective, if capital F is surjective, then small f is surjective. Let's see this. Let's prove this one. If capital F is surjective, then small f is surjective. How to prove it? Capital F is given to you, that is surjective. I need to prove that if this happens, then small f also will be surjective. What is the contrapositive? To prove this, what you do? You just prove the contrapositive. What is the contrapositive of option C? Let's find the contrapositive of option C. You know that every conditional statement is equivalent to its contrapositive. So instead of proving this statement, I can prove the contrapositive. What is the contrapositive of option C? That is, if small f is not surjective, if small f is not surjective, then capital F is not surjective. Okay. So let's see. If small f is not surjective, then capital F is not surjective. Can I prove this? First, what is the meaning of surjection? You understand the definition of surjection first. Let's see the recap. What is the definition of surjection? Surjective function. Surjective function. This is also called onto function. What is the definition of onto function? Very simple. That if f from set A to set B, it is onto function, it is surjective. If and only if for every element of the codomain there is at least one pre-image. Correct? See, I can say if and only if for for all for all y belonging to codomain B, what should happen? There must exist at least one image, pre-image, at least one pre-image. So you can see there must exist at least one pre-image such that you know fx equal to y. Basically, this is the definition. Okay, what I want to say? I want to say that surjective simply means that it simply means that for every element in the codomain, whatever element you take here, it must have at least one pre-image. At least one pre-image. There can be more. There can be many pre-images, but remember there must be at least one pre-image must be there. Okay, very simple. Whatever element you take in the codomain, it should have at least one pre-image. This is the definition of surjective function. Correct? Now, to prove option C, I will prove the contrapositive. The contrapositive is that if small f is not surjective, then capital F is not surjective. Small f is not surjective. What this means? Small f is not surjective. Now, assume this is given to you. Okay, now assume this is given to you, and now this is what we need to prove. Now what is given? That small f is not surjective. What this means? What this means? It means that, remember, small f is from f a to b, correct? This we already know, that small f, this is from set a to set b. Now this small f, if this is not surjective, it simply means that there is at least one element here, there is at least one element which does not have any pre-image. There is at least one element, this element y, this does not have any pre-image, correct? Yes or no? See, very simple point. We are saying small f is not surjective. If small f is not surjective, then there is at least one element y which has no pre-image. There is no pre-image, means there is no element which is mapping to y. Is this clear? There is no element which is mapping to y. I hope you understood this. No element is mapping to y. Clear? So, very simple point here. This is what I'm saying, that like this. Okay. So, very simple. Small f is not surjective. It means that in this codomain there is at least one element such that no element of domain is mapping to y. Okay. Now in this situation, you just tell me what will happen in the capital F. Remember, capital F, this is from power set of A to power set of B. Now where the problem will happen? This is from power set of A to power set of B. Now in the power set of B, you will have this element. Now just tell me one simple point. You just tell me, is it possible that, there is at least one element which is mapping to this element? Just tell me this point. Remember, there is no element of A which is mapping to Y. Yes or no? In the small f, look at this small f. In the small f, in this B, there is this element Y. There is at least one element in the codomain such that it has no pre-image, means there is no element of A. There is no element of A which is mapping to Y. Just tell me a simple point. Just tell me a simple point. From this, you just tell me one thing, that what will happen in the capital F? Capital F, this is from PA to PB. So just tell me, in the PB, this element is there. So who is mapping to this element? Who can map to this element? No one. Because remember, who will map to this element? Element will map to this element, means this individual element will map to Y. But remember, no element is mapping to Y. Do you agree with me? See, I am saying that if some element here, let's assume this, let's assume there is some element here, I don't know which element, but let's assume this element I. Let's assume this element is mapping to Y. Now, what it means? It means that this individual element here inside this element, this has small f image Y, means this small I in the small f, this is mapping to Y. But remember, in the small f, no element is mapping to Y. So did you understand my point? That I am saying that now no one will map to this Y also. Yes or no? So very easy, that's it. So finally I can say that capital F is also not surjective. That's it, hence proved. Did you understand? Very simple, right? Because no element in the small f, no element of domain, no element of A is mapping to this element Y of B. Correct? And now you can easily see that if this happens, means if small f is not surjective, then what will happen? In the capital F, you can see in the codomain, this element has no pre-image. Okay, so that's it. This is what we wanted to prove. So we have proved this option C also. Using contrapositive, we have proved option C. Very simple, right? The proof was very easy. If you notice the proof, it's very easy. Basically, we are just proving the contrapositive. We are assuming, or I can say, it is given to us that small f is not surjective. In the contrapositive, it is given that small f is not surjective. So there is at least one element in the codomain. In the codomain of small f, there is at least one element y which has no pre-image. Means in the small f, there is no element of the domain A which is mapping to this element Y. Correct? So from here you can easily see what will happen in the capital F. In the capital F, in the codomain, there is this element set containing Y, and it will not have any preimage because no one will map to this element. So I can say that capital F, this is also not surjective. That's it. Hence proved. Now let's see option D. If small f is surjective, then capital F is surjective. This is what we want to prove. Okay, now remember, we need to prove option D. Option D is saying if small f is surjective, then capital F is surjective. If small f is surjective, then capital F is surjective. Okay, remember what was option C? That was if capital F surjective, then small f surjective, that we have proven. The option D is if small f surjective, then capital F surjective. So let's see how to prove it. It's quite easy. First, you understand if small f is surjective, then what it means. You know that small f, see, this is given to you that small f is surjective. You know that small f, this is from A to B. Now let's assume that this A has elements A1, A2, and so on an. And this B, this has elements B1, B2, and so on Bm. Okay, so this small f, this is a function from A to B. This. Okay. Now we are saying that it is given that small f is surjective. It means that every element of codomain has at least one preimage. Do you agree? Yes or no? Do you agree that every element of codomain has at least one preimage? At least one preimage. Every element of codomain has at least one preimage. Okay, so whatever element of codomain you take, whatever bi you take, that has at least one preimage. Very simple, very simple. That's it. Now let's see. Now I need to prove that capital F is surjective. This is what we need to prove. That capital F is surjective. Remember what is capital F? This is from PA to PB. Now to prove that this capital F is surjective, what I need to prove? I need to prove that in PB, whatever element you take, that will have at least one preimage in PA. Correct? Okay, means this is what I need to prove, that whatever element you take in PB, if I take any element, let me, for example, let me take, any element, like let me take B3, B5, B6, like that. Okay. Now I need to prove that this element, I need to prove its preimage exists. Okay, is this point clear? You can see this is given that small f is surjective. Now I need to prove that capital F is surjective. Capital F, this is from PA to PB. Now I need to prove that in PB, whatever element you take, that will have at least one preimage in the PA. So basically, I need to find the preimage of this B1, B5, B6. What will be the preimage of B1, B5, B6? This is very easy. What you do? You already know that B1 has a preimage. This B1 has a preimage because you can see small f is surjective. So every Bi has a preimage. So you can see B1 has a preimage, B5, B6, all of them, they have preimage. So what you do? How to find the preimage of this set? To find the preimage of this set, what you do? For each individual element, you find the preimage, and that's it. Okay, I hope you understood. See, what I need to do, I need to find the preimage of B1, B5, B6. So how to do that? Already this is given that small f is surjective. So I can say that every Bi, so I can say every Bi, every Bi that belongs to B. Of course, this f is from A to B. Okay, so you can see that every Bi has at least one preimage. At least one preimage. Okay, let's assume that for Bi, yeah, okay, don't assume anything. So you can see every Bi in the codomain B, it has at least one preimage in domain A. Okay, this you already know. Now you take one, you do one thing, that To prove that this F is surjective, what you do? You take element of the codomain. Okay, basically take any element of codomain. Take any element of the codomain, right? So if I take any element of codomain is PB. Okay, codomain is PB. And if I take any element of codomain, so that will be subset of B. Okay, do you agree? So you can see that very simple codomain, that is PB. Okay, so if I take any element of the codomain, that will be subset of B. Any element of the PB, that is subset of B. So you can see, take any element S. So I can say this S will be subset of B. So take any such S. Basically, take any such S you take. Now I will prove that this S. Now we will show. Now what we will do? We will show at least one pre-image. We will show a pre-image for S. This is what we will show. Okay, so remember, you take any element in the codomain, you take any element in the codomain PB. Of course, any element in the PB, that is subset of B. So you take any subset of B, we will show a pre-image for S. This is what we are going to show. And how to do that? Very simple. This S you are taking PA to PB, and here you are taking some, take any S here, take any S that belongs to codomain. Now I will show that this S has a preimage. For example, there are two cases. Case one, if this S is empty, and the case two, if S is not empty. Okay. Now remember, if S is empty, then it's very easy. You know that the preimage, will be empty set. You know, 5 maps to 5. Okay, that we have already seen. So you can see that preimage of S, that will be 5. Okay, is this clear? So we found the preimage of S, that is 5. Very simple, 5 will map to 5. Now if you take non-empty S, then what it means? It means that S is looking something like this. In the S you have maybe, B1, B3, maybe B6, like that. Okay, this is just for example I have taken. Okay, basically S looks like this. Okay, for example I have taken this. For example, just for understanding purpose, you basically take any set S you take in the PB. Okay, so let's assume that this set I have taken in the PB. Now what will be the pre-image? What you will do? What will be the pre-image of S? Let's see the pre-image of S. That's very easy. What do? You find the pre-image of B1. Is there a guarantee that B1 has a pre-image? Is there a guarantee that B1 has pre-image? Yes, there is a guarantee, because small f is surjective. So every BI has a pre-image. Every BI has a pre-image. This we have already seen. You can see small f was surjective. Small f is surjective. So I can say every element of capital B, or I can say every BI has at least one pre-image. Every BI has at least one pre-image. So you can see that this B1 also has pre-image. Yes or no? So definitely B1 has at least one pre-image. Okay, you can see here, for example, in this diagram, you can notice that this B1 has pre-image A1, A2. Okay, so what I can do? You just put the pre-images of B1. These are A1, A2. Okay, its pre-images for B1. These are the pre-images of B1. Let me write here that these are the pre-images of B1. These are the pre-image of B1. Okay, similarly, you can see you write the pre-images of B3 also. Is there a guarantee? Can you give a guarantee that B3 has at least one pre-image? Can you give this guarantee that B3 has at least one pre-image? Yes, B3 has at least one pre-image, because every BI has at least one pre-image, because small f was surjective. Yes or no? And similarly, you write pre-image of B6 here. pre-image of B6 you write here. That's it. Basically, the idea is very simple, that you take any S. In that S, if that S is empty set, then the pre-image will be empty set. Phi will map to phi. So for phi, the pre-image is phi. Okay, very simple. And if S is non-empty, then what you do? For each Bi, you just write the pre-image. And remember, for each Bi, there is a guarantee of having a pre-image because small f is surjective. So you can see that every Bi that has at least one pre-image. So what to do? For each Bi, you just write the pre-images. Now this set that you will get, this set will definitely, you can see, this will map to S. Yes or no? So this is the pre-image. This is at least one pre-image of, this is a pre-image of S. Okay, I hope you understood this point. So you can see for this S, we have found pre-image, or I can say that this will map to S. So I can say that this capital F, this is surjective. Okay, so this is what we wanted to do, that we will show at least one pre-image of S. That's how we prove that capital F is surjective. That's how we prove capital F is surjective. Okay, so that's it. I hope you understood. See, the proof was very simple. We are just showing that to prove that capital F is surjective, what to do in the codomain. In the codomain, you take any element. That element, of course, that will be subset of B. So you take any element, you take, and you just find its pre-image. And you can see easily we can find the pre-image because you know that every Bi has at least one pre-image, because small f, which is from A to B, this was surjective. So you can see every Bi, whatever Bi you take, every Bi has at least one pre-image, at least one pre-image. Okay, every Bi has, at least one pre-image. So you can see that for this element, you can find the pre-image. How to find? Very simple, that for each Bi, you write the pre-image. If you write like this, then this pre-image you will find, which will, of course, which will map to this. Okay, so I hope you understood. So I can say that this capital F, this is surjective because every element of the codomain has at least one pre-image. And I have shown to you how to find at least one pre-image for any element of the codomain. Okay, this is how you can find. I hope you understood. So that's it. We have proven all the four statements. So all the four statements are true. So this is the complete explanation. This is the complete analysis of this question. So please tell me, did you understand? Let me know. What do you think? All the four options are like four questions. So did you understand? Please tell me. Let me know. Let me tell you this question. For this question, we have done the complete analysis for each option. Each option we have discussed like a separate question. First, we have understood the question, what the question was saying. First, we understood that with help of some examples. Then we have taken each option as a separate question and we have done the complete analysis. I have provided you the proof also. And now let me tell you that this question, this is really a beautiful question. Similar questions have already come in the GATE exam, in the GATE CS. Already similar questions have come in the past in the PYQs. And this question has the potential of coming in the future. This question is taken from IIT Kharagpur and this is really beautiful question. It's not hard. To be honest, this question is not easy also, not hard also. This is moderate type of question. Did you understand the explanation? The explanation that I provided to you, did you understand it? Just take your copy pen. If you did not understand, just take your copy pen and watch this video again. For any option, if you did not understand the explanation, then just watch the video again and take your copy pen and do it. The way I am doing it, you also do it. Step by step, the proof I've told you for each option. Okay, I have told you everything, like what this means, what this means, what this means. For every small thing, I told you what this actually means. Okay, so how we are proving all these four options, how we are proving. So I hope you understood the proof of each and every option. And I hope you enjoyed this question. I hope you loved this question. This definitely has a potential of, coming in the future GATE exam. Maybe someday, maybe after a few years, maybe this question can come. But this question, I can say that it is moderate. or I can say moderate to hard, but it is not actually hard, because you can see once you go through the solution, then you will find that this is either moderate or moderate to hard. Not easy, not hard. Okay. So please tell me, did you understand? Only one student is saying that this student has understood. Of course, in the live chat there are there are very few students right now. Okay, because it's very late at night. I can say at this moment it's almost 1 a.m. But just tell me, all the students who have watched this complete solution that I provided, did you understand? Please share your feedback. If you are watching this as a recorded session, not as a live session, if you are watching this in the recorded format, then please put a comment. Please share your feedback with me. Did you like this question? Did you understand the solution? Did you understand the proof? Each option, did you understand the explanation, the complete explanation? Did you understand? So please share your feedback with me. Okay, your feedback matters a lot. So just let me know. Did you understand? Okay. So thank you, everyone. Remember, if you find this session, if you find this analysis, if you find this solution helpful, then please like, comment, and share. Please put a comment. Please let me know, did you understand? And remember, your support will decide the future of our Go Classes YouTube DPP series for Gate CS, Gate DA. If you participate, if you show interest, if you share, if you like, if you comment, then we will keep bringing new unseen standard questions to solve. On the YouTube, in the search box, you can search Gate CS DPP or Gate DA DPP. Okay, so Gate CS DPP Go Classes you can search, and this playlist you can check it out. This is Go Classes YouTube DPP series playlist for Gate CS. You can see GOT DPP series Gate CS. The complete playlist you can check it out. You can see in the description, also in the pinned comment, this playlist link you can find. So do check it out. For Gate DA aspirants on the Go Classes Gate DA YouTube channel, we have started the DPP, the YouTube DPP series for Gate DA also. So visit our Go Classes Gate DA YouTube channel. On YouTube, you can search Gate DA DPP, or on YouTube, you can search Go Classes Gate DA. Then this Go Classes for Gate DA, this YouTube channel, you can subscribe. And on this YouTube channel, you can find the Gate DA YouTube DPP series also. Okay. So thank you, everyone. You can see this was the question. This was the original question from the IIT Kharagpur. Basically, you can see this is the question, and they are asking you to prove. You can see prove the following. They are saying that prove the following. You can see capital F is injective if and only if small f is injective. And option B is, or I can say part B, that is, we need to prove that capital F is surjective if and only if small f is surjective. And remember, once you have done these two, then you can also say that capital F is bijective if and only if small f is bijective. Correct? What is the reason? Because bijective means injective and surjective. See, we have proven this also, we have proven this also. These two we have proven. Okay, we have proven if also, only if also, if also, only if also. Basically, total 4 questions we have done. All these 4 questions. Now, what is bijective? Bijective means injective and surjective. So already we have done these 4 questions. These questions already we have done. So automatically I can say that capital F is bijective if and only if small f is bijective, because we already know that bijective means injective and surjective. We know that capital F is injective if and only if small f is injective. Capital F is surjective if and only if small f is surjective. So I can say that capital F is bijective if and only if small f is bijective. So remember, from the part A, from the part B together, you can say that you have proved part C also. I hope you understood. So these three part A, part B, part C, all the 3 parts we have proved. Okay, so that's it. So thank you, everyone. I hope you enjoyed this session. Thank you.